Hello, welcome to the ChemDoctor, and the purpose of this video is to start filling in on some of the basics that I don't yet have on my website. And I noticed when I looked at the different links that I'm missing a very basic description of the atoms. So that's what this video is going to focus on. All right, so you open up any textbook, whether it's a high school textbook in chemistry or a university level general chemistry textbook, and the first thing that they're going to tell you is that the atom is composed of basically three subatomic particles: the protons, the neutrons, and the electrons. All right, and furthermore, they're going to tell you that the protons have what they call a positive charge on them. The electrons have a negative charge. I separated the electrons a little bit away from the protons and the neutrons because I think it's important for you to realize from the get-go that the protons and the electrons are the protons and the neutrons are responsible for over 99.99% of the mass of an atom. All right. It's not that the electrons are massless. They have a mass, but they're about 1,000 times lighter than a proton or a neutron. And the protons and the neutrons essentially have the same mass. So together, the proton and the neutrons constitute the majority of the mass of any given atom. Now, in this day and age, we know fully that these subatomic particles can be broken down into even smaller particles. But here's the deal. This video is not going to venture across those boundaries into those areas, because for a generalized high school chemistry course or a university level general chem class, you're never going to be looking at anything atomically that's going to be beyond the protons, the neutrons, and the electrons. And so this video is going to focus on the atom as if the atom is the smallest unit of matter. Now, even as I say that, we know it's not true. But like I said, for these kinds of courses, we're going to assume that, because everything that we're studying beyond this is macroscopic by comparison to the subatomic particles that are within these subatomic particles or within the nucleus of the atom. All right, now I want to just briefly mention the issue about stipulating the charge on the proton and on the electron. What you need to realize about the charges: the positive and the negative don't have a physical meaning. What this dictates, or what this designates to us, is that the proton and the electron have a mutual attraction for one another. So if you put an electron somewhere in the proximity of a proton, they're going to be drawn together because they share a mutual attraction for each other. All right, and we could have indicated that mutual attraction by calling the proton a blue particle and calling the electron a red particle, but the charges were given this designation a long time ago. So the positive charge on the proton doesn't mean that the proton is lacking something, and the negative charge on the electron doesn't mean that the electron has something extra. It simply means that the proton and the electron, by virtue of the fact that they have different charges, are mutually attractive. The neutron has no charge, so I'll just put a 0 here to emphasize that. So the only thing that the neutron is bringing to the atom on a macroscopic level is mass. The proton is bringing mass and a charge, the mutual attraction for electrons, and the electrons, essentially because they're so light, are bringing the charge. Now let's take a look at an example here where we compare two identical atoms of the same element. All right, and the one I'm going to focus on is going to be carbon. So if you glance at a periodic table, most periodic tables are going to look like this. If we take the box out of the table and we glance at it, the number that is above the atomic symbol is what we call the atomic number. And the atomic number gives us the number of protons So the number of protons that you find in an atom designates what that element is. So there are no elements on the periodic table other than carbon that have 6 protons. If you have an element that has a different number of protons, it can't be carbon, it has to be something else. This number down here is what we call the atomic mass. And I'm going to leave that as a discussion for later. You can already find several videos that I have on my website that describe this number. What I'll say right now about it is that you notice that it's a decimal, and that's because this atomic mass is actually a weighted average of different particles, and I'll come back to that in a second on a simplistic level. So let's take a look at a carbon atom. All right, so the first thing I'm going to do is, and I'm not drawing these dots in any specific order. What I'm doing is putting them in to make a point. So we're going to designate my protons here as being the black circles. So for carbon, there's 1, 2, 3, 4, 5, 6 protons. All right, and I'm going to designate my neutrons with this color. All right, and for this carbon atom, we're going to scroll in here a total of, let's see, what do I got here? 1, 2, 3, 4, 5, 6 neutrons. And then, not to ignore them, I'm going to go ahead and put in the electron clouds for carbon. All right, which are going to look something like this in essence. All right, and remember that the electrons are not part of the nucleus. And there's going to be a total of 6 electrons, so I'm going to go ahead and put them in. There's going to be 4 of them in this outer shell, and there'll be 2 of them in here, like that. All right, so this is what we call, now, let's quickly define, I'm going to quickly define a concept here called mass number. And mass number is equal to the number of protons plus the number of neutrons. Number of neutrons. So you can see for this carbon atom, there's 6 neutrons, and there's 6 neutrons in the outer ring here. This isn't really a ring. Like I said, there's really no order here. What I'm trying to do is just blatantly illustrate what the nucleus is going to look like in terms of what particles are in there and how many. So you can see that we've got 6 neutrons here, which I'll call this, and then we've got 6 protons. So the mass number of this particular carbon atom is 12. And we can list this thing as C12. All right, now let's take a look at another example of a carbon atom. All right, again, like I said in the beginning of the video, all right, the number of protons designates who this is. So if it's carbon, there can't be any more than 6 protons. So I'll put them in. Now, in this one, however, and this is true for all atoms, the number of neutrons can vary. So in this one, what we see is happening is there's going to be a total of 7 of them. All right, and again, I'll just whip in the electrons here in an electron cloud that's actually in 2 parts. All right, we're going to have, a couple of electrons in here, and we're going to have the other 4 that are going to be out here. Note, I'm illustrating something with the electrons that I didn't point out at the beginning, and that is that for a neutral atom, so let me define that over here, a neutral atom has no charge on it. No charge. The only way that that can happen is that the number of protons equals the number of electrons. So you'll notice in both of my atoms here, both of my atoms of carbon, there are 6 protons, and there's also a total of 6 electrons. 1, 2, 3, 4, 5, and 6. And if you count on this one, you'll see the same thing. So let's take a look at this carbon atom here and compare and see what the difference is between the two. So when you count the neutrons, there's 7 of them. There's still 6 protons. There has to be. If there's not 6 protons, it's not carbon. And we have a mass number of 13. So we would call this C13. All right, another way of representing these two atoms of the same element that have different numbers of neutrons would be this way. You'll see this notation in subsequent videos. It's called AZE notation. And I can put my atomic number, or the number of protons, in like that. You can see very simply, if we take the difference between these two numbers, you're going to get the numbers of neutrons. Now, what do these two elements represent? They represent what we call isotopes. Okay, so an isotope are an element with a different number of neutrons. So these two carbon atoms are identical in every way except for mass. Now, you say to yourself, well, how does this work then if we were to dig up a chunk of carbon out of the Earth's crust? What would we see? Well, if you were to take that chunk of carbon and smash it up into small pieces, and then smash those pieces into smaller pieces and keep on smashing until you could spread a layer of carbon atoms out on a table, and if you could circle, if you could put a circle around 100 of those atoms, and I'm just going to illustrate this here somewhat like this. So if we could circle 100 of these atoms, what you would find out is about 99 of them are C12s, and about 1 out of every 100 is going to be C13. So when we sum together the total masses of a sample of carbon, what's going to end up happening is we're going to get a weighted average. And that's where the atomic mass comes from. And that's why it's in the form of a decimal. All right? And with that, I'm going to go ahead and close the video.